Okay, hello everyone. So now we're solving homework number 4, CHEN 422, Chemical Reaction Engineering. If you recall, this week we talked about size comparison for different reactors. We talked about, comparing CSTR to PFR, equal size CSTRs in series, unequal size CSTRs in series, PFRs in parallel, PFRs in series, etc. And this homework is a reflection of the type of problems you're going to see. So let's start with the first one. Problem number 1 here, a liquid reactant stream, 1 mole per liter, passes through 2 mixed flow reactors in a series. The concentration of A in the exit of the first reactor is 0.5 moles per liter. Find the concentration in the exit stream of the second reactor. The reaction is second order with respect to A, and V2 over V1 equals 2.5. Okay, so let's go to the whiteboard and let's just start setting it up. Okay, let me open the whiteboard here. Okay, and let's start. So this is homework 4, CHEN 422, and problem 1. So in this problem, I have 2 CSTRs, right? And this is the second CSTR here. And I'm given some information, so you're told CA note to this unit is 1 to the first CSTR is 1 mole per liter. The concentration of the outlet of the first CSTR, I'm going to call the CA1. It's 0.5 mole per liter. And you need to find the concentration leaving the second CSTR. You're given some other information, specifically, so this will be CSTR1, and this is CSTR2. You're being told that V2 is equal to 2V1, and it is it's a second order reaction, i.e. minus RA, we're just using A to denote the species, is equal to K Ca squared. Okay, so I want to find the CSTR leaving the second reactor. So let's start by using, our starting point will be the CSTR performance equation. Okay, so let's start with the performance equation for a CSTR. If you recall, the CSTR performance equation is V over FA 0 is equal to tau over CA0 is equal to basically XA over minus RA, or second order kinetics. So I'm going to rewrite this as XA over K Ca squared, right? I just substituted it right here. And instead of XA, I'm going to use the definition of XA. So I'm going to write this as 1 over K Ca squared multiplied by Ca naught minus Ca over Ca naught. And the logic here, because I'm given everything in concentrations, so I'm just going to rewrite my equation in terms of concentration for it to make sense. Okay, so now I'm going to use this term right here and this term right here. So let's rewrite our clean equation basically. Let's call it this way: tau over Ca naught is equal to 1 over K Ca squared multiplied by Ca naught minus Ca over Ca naught squared. And this guy cancels with this guy. I'm going to move K to multiplied by tau to get the dimensionless parameter, which basically we can use to compare volumes, right? So I'm going to say tau K is equal to Ca naught minus Ca over Ca squared, okay? And this will be the equation I use to solve this problem. So let's look at the first CSTR. So let's look at CSTR1 now. I'm going to write the equation as tau1 k is equal to Ca naught minus Ca1 over Ca1 squared, right? And I can plug in numbers at this stage, so I have Ca naught, it's basically 1, right? 1 minus 0.5 over 0.5 squared, and this is equal to basically 2, right? Because this is half, half cancels with half, 1 over 0.5 and 2. Okay, and now let's look at CSTR2. And in this case, tau 2k is equal to Ca naught to the second CSTR is actually Ca1, right? So for this one, it's going to be Ca1 minus Ca2 divided by Ca2 squared. Okay, and in this case, I only have one. Ca1 is 0.5. I don't know what Ca2 is. So we're gonna, we have to solve for Ca2. Okay, so I have CSTR1, CSTR2. Let me number these pages. So this will be, I'm gonna write here, page 1. And let me save it. And now let me just erase erase the stuff we wrote here so that you can solve the problem. Okay. So this is page 2. And now I'm gonna restart here at the top. So I have these two expressions right here. If I restart here, I'm gonna divide them. So if you recall, at constant density, and epsilon equals 0, this expression becomes valid, where I basically have tau 2 k over tau 1 k is equal to v2 over v1. And I'm given that v2 over v1 is equal to 2. This is given, right? So I'm gonna substitute the expressions for tau 2k and tau 1k. So I'm gonna get basically, so Ca1 here is 0.5, right? So I'm gonna rewrite it directly. So I have 0.5 minus Ca2 divided by Ca2 squared over 2. And if I rearrange this, I'm gonna get 0.5 minus Ca2 over Ca2 squared is equal to 4. And this basically gives me 4 Ca2 squared plus Ca2 minus 0.5 equals to 0. So I have a little quadratic here. So this is what? 4 Ca2 minus 1, right? Multiplied by Ca2 plus 0.5 is equal to 0. This makes sense. 4 Ca2 squared plus 2 Ca2 minus Ca2, so I get a 1 here, plus 0.5. So which one? So this won't give me, so this Ca2 is equal to minus 0.5 is junk. I don't care about it. And this is the answer I'm looking for. Ca2 is 0.25 mole per liter. Okay. And this is the answer for this problem. Okay, so this is the solution for problem number 1. Again, in this problem, you're given 2 CSTRs. You're given the concentration at the inlet of the first CSTR, the outlet of the first CSTR, and you need to determine the concentration at the outlet of the second CSTR. You're given a piece of information about the volumes, and this is really where you solve the problem. You rearrange the performance equation to get the dimensionless quantity, tau 1k, and the ratio of dimensionless quantities is equal to the ratios of the volumes, which is right here for constant density problem. So this is what we did. I just put in the information I have and I solved for CA2. Okay, so this is number 1 done, saved. Let me clear everything here. And let's go back to the homework. Let's have a look at problem number 2. Problem number 2, you're being told an aqueous reactant stream 4 moles of A per liter passes through a mixed flow reactor followed by a plug flow reactor. Find the concentration at the exit of the plug flow reactor if in the mixed flow reactor Ca equals 1 mole per liter. The reaction is second order with respect to A, and the volume of the plug flow unit is 3 times that of the mixed unit. Okay, so I have a mixed flow reactor followed by a plug flow reactor. Ca note is 4 moles per liter. In the mixed flow reactor, Ca is 1 mole per liter. You want to find the concentration at the exit of the plug flow reactor, and you're also being told that the plug flow unit is 3 times that of the mixed flow unit. Similar problem to the one above, except in this case, instead of having 2 CSTRs, I have a CSTR followed by a PFR. Okay, let's go to this board here. So this is page 3 and number 2. Let me first of all draw a little diagram. So in this case, I have a CSTR, and the outlet of the CSTR enters a PFR this way, and you're given Ca note. We said is 4 moles per liter. Ca here, I'm gonna call this Ca1. You're told it's 1 mole per liter, and you need to calculate Ca2 basically, and you're given a piece of information. You're told the volume of the PFR is 3 times the volume of the CSTR, and again you have second order kinetics. So basically minus RA is equal to K Ca squared. Okay, so I have a CSTR, I have a PFR, right? So this one is a CSTR, this one is a PFR, and I need to resolve them. So I need to compare the volumes, right? I need to use this piece of information somehow to solve this problem. Okay, so let's do it. Let's start off by writing, and sorry, so in order to compare these volumes, I need to get the dimensionless quantity, right? Tau k. In order to get tau k, I need to start from the performance equation. So this is exactly what we're doing. I'm going to start with the performance equation. For the CSTR. And the performance equation, we said, tau over Ca naught is equal to XA over minus RA. And similar to the previous problem, I'm going to rewrite XA. So I'm going to write RA, first of all, as 1 over K Ca squared. And then I'm going to rewrite XA as Ca naught minus Ca over Ca naught. And basically, this Ca naught cancels with this. I'm going to move the K to the other side. So I get tau CSTRK is equal to Ca naught, in this case, Ca, we're going to use Ca1 to avoid confusion, over Ca1 squared. And if I plug in the numbers, so Ca1 is 1. So I'm going to get basically what? 4 minus 1 over 1 is equal to 3. Okay, so tau CSTRK is equal to 3. Now let me do the same thing for the PFR. So I have performance equation for the PFR, right? So if you recall, performance equation for a PFR is tau is equal to minus integral CA. In this case, the inlet is CA1, right? CA1 to CA2 of dCA over minus RA. If I plug in the numbers, I'm going to get integral CA1 CA2 of dCA over K CA squared, and this will be what? Let's take the K out. Minus 1 over K. I'm going to get integral of 1 over CA squared is what? Minus 1 over CA, right? Minus 1 over CA from CA1 to CA2. And if I, so now tau PFR in this case, let's be careful with all these negatives here. Minus 1 over K and minus 1 over CA2, minus, so plus 1 over CA1. I'm gonna just distribute this minus inside. So I get 1 over CA1 minus 1 over CA2 multiplied by 1 over K. So tau PFR K is equal to 1 over CA1 minus 1 over CA2. Okay, so I have an expression for tau PFRK and I have an expression for tau CSTRK. So now this should enable me to solve this problem by using this equality, this piece of information right here. So let me save this. Let me erase this figure. And now this will be page 4. Right? Okay, let me erase. So now I'm gonna take these two and go here. So I'm gonna say that tau PFRK over tau CSTRK is equal to V PFR over V CSTR, and this is valid assuming constant density and epsilon equals 0 is equal to 3. And this will be equal to what? So I'm gonna have 1 over CA1 minus 1 over CA2 divided by tau CSTRK is equal to 3. So now I just have an algebraic problem. Let me cross multiply here, and so I have 9 is equal to 1 over CA1 minus 1 over CA2. CA1, this guy is 1, right? So this guy is 1. Is it 1? Yeah, this is 1. Did we do a calculation? Do we have an error here? Let me just double check. Yes, we have a small error here. It's just, let's try to fix it. Because what I did here is 1 over minus 1 over K minus 1 over CA2 plus 1 over CA1. For some reason, I just, I don't know what happened. Anyways, it's wrong. Just be careful. Let's rewrite it. These have to be flipped. Let's rewrite them everywhere. Yeah, I have a feeling we're gonna mess all these negatives up. Okay, so minus, this is CA2 minus CA1. So this is equal to CA2 minus CA1, right? And here this becomes CA2, CA1, CA2, CA1. 1 is given to be 1. So basically 10 is equal to 1 over CA2. So CA2 will be 0.1 and the units are mole per liter. And this is the answer to problem number 2. Is this what they're asking for? Yes, find the concentration at the exit of the plug flow reactor. So that concentration will be 0.1. So we did a small error here, distributing this minus. Again, just be careful with these types of problems. Try to be, on exam day at least, try to be very sharp and catch the errors, when you're proofreading or when you're revising your calculations, just maybe take a closer look. Okay, good. Let's move on to the third problem. Okay. Let's have a look here. Reactant A plus R. This has to be A goes to R. And Ca note equals 26 mole per meter cubed, passes in steady flow through 4 equal sized mixed flow reactors in series, and tau total is equal to 2 minutes. When steady state is achieved, the concentration of A is found to be 11,521 mole per meter cubed in the 4 units. For this reaction, what must be tau plug so as to reduce Ca from Ca note 26 to Ca final to 1 mole per meter cubed? Okay, so you're given a reaction, A goes to R. You're given an initial concentration, 26. You're being told it goes into 4 equal sized CSTRs with an overall space-time of 2 minutes. And you're being told at steady state, the intermediate concentrations are 11,521. And you're being asked, what is the equivalent space-time in a plug flow to achieve the same conversion, right? So for this reaction, what must be the space-time in a plug flow so as to reduce Ca from Ca note 26 to 1? Okay, let's go to the wording is a bit, these problems are taken from Levenspiel, and yeah, he tends to use his wording can be a bit clunky at times. Okay, anyways, I think this is page 5. So we're doing number 3, and we're being told we have A goes to R, and I am doing this in 4 equally sized CSTRs, right? So this is the first CSTR. Goes into second CSTR, right? Goes into third CSTR, and then goes into a fourth CSTR right here. Okay, and you're being told that you're given some information. Ca note here is 26 mole per meter cubed. You're also given Ca1 is 11 mole per meter cubed. Ca2 is 5 mole per meter cubed. Ca3 is equal to 2 mole per meter cubed, and Ca1 is equal to 1 mole per meter cubed. And you're being told that tau total is equal to 2 minutes. So if tau total equals 2 minutes and they're equally sized, so because they're equally sized, then this means that tau of I is equal to 2 over n, 2 over 4, so 0.5 minutes, right? So the residence time in each of these reactors is equal to half a minute because, they're all equally sized. So the fluid will spend the same amount of time in all of them. Okay. So what are we being asked? So you need to find the tau for a PFR equals what? for CAF to be equal to 1 mole per meter cubed from a CA note of 26 mole per meter cubed. Okay, if you go to your slides, we discussed this when we talked about, when you have n number of CSTRs in series, they start behaving like a PFR, right? If you recall in your slides, we said n CSTRs in series, they behave like a PFR, and we have two equations in that case, right? The first equation we have in these slides is for CSTRs in series. So we said for equally sized, of course, for CSTRs in series, we said that CA note over CAF is equal to 1 plus K tau I to the power n. And if you recall, what we did is, CA note over CA1 multiplied by CA1 over CA2, CAN minus 1 over CAN, and all these guys cancel out in the middle, and you just end up with this final expression. So in this case, what do I have? I have CA note, right? I have CAF, and I have N. So I can get, and I have tau actually. So I can get K, right? Okay, so using this equation, I can get K from this equation because I have everything else. So what am I going to do with this K? I need to find the equivalent tau for a PFR, for a first order reaction. So if you recall, for a PFR with a first order irreversible reaction, we said that CA note, or actually for a PFR, it's reverse. CA final over CA note is equal to exponential of minus K. And this equation is valid. You can double check if you want, but it's valid for a first order PFR. If you recall, the performance equation for a PFR is what, if you want to derive it quickly on the side here, is basically tau over CA note, and this is equal to integral dxa over RA, or integral CA over KCA. You're gonna get ln CA. You move it to the other side, now you're gonna get exponentials. You can verify this at your own time, but this equation is valid, or you can remember it, in an exam. You just want to use this equation for a first order irreversible reaction. It's in your slides. You can go ahead and use it directly. Anyways, so the strategy here is that in this equation I have CA note CAF, can get K, and then this equation I have CAF CA note, I can get tau. So let's do this. Let's use this approach. Okay, so let me save. Let me erase this figure here at the top, and let's continue working at the top here. Okay. So this will be 6, right? 6. And let's continue in red. So I'm going to start with this equation. So I have CA note over CAF is equal to 1 plus K tau I to the n. So basically CA note was 26, CAF was 1. is equal to 1 plus K. We said tau was 0.5. 0.5, N was 4 because I have 4 equally sized CSTRs. So if I just do this, I'm going to get K will be equal to 4th root of 26, right? Minus 1 multiplied by 2 or divided by 0.5. And if you do the calculation, you should get this is equal to 2.516. And because it's a first order reaction, the units here will be 1/2. Okay, so just from your first lecture, just you should be able to know the units of the constant and of the reaction rate for any order reaction. Okay, so I use the first equation, I have K, so now let me use the second equation, CAF over CA note. Am I sharing the screen? Is equal to exponential minus K tau, and CAF was 1. Here, CA note is 26. So if I take a normal ln 1/26 is equal to minus K tau, PFR of course. So this means that tau PFR is equal to minus ln 1/26 divided by 2.56. And in this case, you should get tau to be equal to 1.29 minutes. Okay, so this is the answer to this problem. And one thing to note is that, for 4 CSTRs, the tau was 2 minutes. For 1 PFR, to achieve the same thing, the tau was 1.29. If I increase my CSTRs, the residence time will be eventually less, and you'll approach the same performance, whatever it is, but the PFR still performs better in terms of residence time if you use it as a metric. Okay, so this is problem number 3, right? Yeah, this is problem number 3. So let's move on to number 4. Let me save this. Let me clear all my drawings, and let's go back to the homework. Problem number 4, sorry. Let's read it here. Originally, we had planned to lower the activity of a gas stream containing radioactive xenon-138, half-life 14 minutes, by having it pass through 2 hold-up tanks in series, both well mixed and of such size that the mean residence time of gas is 2 weeks in each tank. It has been suggested to replace the 2 tanks with a long tube. What must be the size of the tube compared to the 2 original stirred tanks? And what should be the mean residence time of gas in this tube for the same extent of radioactive decay? Okay. So we're given radioactive decay, which is first order kinetics. You're given some half-life information, which you can use to get the K value. You're told I'm passing it through 2 CSTRs, well mixed, and residence time is 2 weeks in each tank. And it has been suggested that we replace the 2 tanks with a long tube, so a large PFR. What must be the size of this PFR compared to the 2 original stirred tanks? And what should be the mean residence time of gas in this PFR to get the same extent of radioactive decay? Okay, so let's have a look at this problem here. Let's go back to the whiteboard. And this, I believe, page 7 is problem 4. And in this case, basically, I have 2 CSTRs. C note, C1, C2, whatever. And you're being told it's radioactive. So radioactive automatically means it's first order kinetics. And if you recall from the first slide, K for radioactive material is basically ln2 over T to the half, which is the half-life. So if I go ln2 divided by 14 minutes, the K in this case is 0.495 minutes, right? Okay, so I have the value for K. Sorry, minutes minus 1. So be careful with the units in this case. And you're given that the tau in the first reactor is equal to the tau in the second reactor. And this is equal to 2 weeks. So tau 1 is equal to tau 2 is equal to 2 weeks. So one thing I'm going to do, I'm just going to convert this to minutes directly because this guy is in minutes and I don't want to forget. So 2 weeks, 7 days a week, 24 hours a day, 60 minutes, 60 minutes an hour, right? Let me just get this calculator guy here. Okay, 2 by 7 by 24 by 60. So I get 20160 minutes. Okay, so this is tau. And what am I looking for actually? What does the problem want us to do? Let's go back to the problem. Forgot already. It has been suggested that we replace the 2 tanks with a long tube. What must be the size of this tube compared to the 2 original stirred tanks? And what should be the mean residence time of gas in this tube for the same extent of radioactive decay? Okay, so I need to find the residence time of a PFR, which will achieve the same effect. And I need to find the, its size compared to these CSTRs. Okay, so I need to find 2 things. Let's just rewrite them, write them here. I need to find tau PFR decay and to volume PFR over volume CSTR. So this is very similar to the previous problem, right? We're comparing CSTRs in series versus a PFR. And because the residence time is the same, so we can say that, they're equally sized or very similarly sized. So I'm going to use the same equation, which is what we said, CA naught over CA final is equal to 1 plus K tau I to the N. And in this case, this will be CA or C naught, if we're using C naught, using this notation at the top here. So this will be C naught over C2 is equal to 1 plus K, and tau I is 20160. All of this, N is 2 squared. So in this case, I can get an expression for C naught over C2. You can calculate it and get a number if you want to. What I'm going to do is I'm just going to use the second equation directly. So this is for CSTRs in series, and then PFR, first order, reversible. So the equation is, it's actually CA final over CA naught. Just be careful that these are reversed. Okay, if you want to write them, if you want to write this as 1 over or minus N and save any confusion, you can do that. But if you're not going to do it, just be careful, okay? Exponential minus K tau PF4 and CAF over CA naught. This is equal to C2 over C naught, and this is equal to 1 over 1 plus going to substitute the value for K directly, 0.495 into 20160, all of this squared. So now I can solve for tau, because I know K in this case is 0.495. Just take ln both sides, just do some math, whatever, and you're gonna get tau PFR to be equal to 279 minutes minus 1. Okay, so this is the tau for the PFR to achieve the same thing, and volume PFR over volume CSTR will be basically, I need to do, just to recall that V PFR over V CSTR is equal to, for a first order, is equal to tau PFR K over tau CSTR K. And if you divide 279 by 2 of this, you're going to find out that it's almost, you're going to need a much smaller PFR, right? Because this will be, because the K's cancel out, it's the same number. 279, unless I did a mistake here in the calculation somewhere. 2 into 20160. And this will be a very small number. I'm going to pause for a second, just verify this using my calculator and come back. Okay. Yeah, this number is correct. I just have an error here. ln2 divided by 14 is actually 0.0495. So just be careful. Hopefully you're calculating it and not just copying these numbers. But if you are, just 0.0495. I'm gonna do this calculation. I'm gonna get 279 minutes minus 1. So if I compare the volume of PFR to a volume of a CSTR, in this case, I have to divide 279 by this number. So I'm gonna get so you divide 279 divided by 2, and then divide by 20160. You're gonna get 6.9 times 10 to the minus 3, right? So the PFR will be significantly smaller, will require a lot less holdup to achieve the same type of concentration. Okay, so this is problem number 4. Let's let me save this, and let's move on to the next problem. Let me clear this all the drawings here. Let's move on to the next problem. Okay, so now we're doing problem number 5. Problem number 5, you're being told at present we have a 90% conversion of liquid feed n equals 1, Ca0 is 10 to our plug flow reactor with recycle of product. So I have a plug flow with recycle. If we shut off the recycle stream, by how much will this lower the processing rate of our feed to achieve the same 90% conversion? So I need to compare two cases. The first case when there's no recycle, second case when R equals 2. Okay, let's go to the whiteboard. I think this is page 8, right? And this is number 5. So I'm given a PFR. Okay, just draw it properly. And I'm given some information. So I'm told n equals 1, it's first order. I'm told XA is 0.9. I'm given CA note is 10 mole per liter. Right, is it 10? Yeah. And I'm told that I need to compare the performance of this versus the performance of a recycle with R equals 2, right? So if I have a recycle stream here and R equals 2, I need to compare basically the tau of the recycle versus tau of the no recycle. Okay. So again, it's a first order reaction. So if you recall, the performance equation for a PFR with recycle, and this is in your slides. Performance equation is this. V over FA0 is equal to tau over CA0 is equal to R plus 1 integral of from R XAF over R plus 1 all the way to XAF of dXA over minus RA, and in this case minus RA, and because it's first order, I'm gonna just rewrite this directly in the first order form, which is what K CA naught of 1 minus XA, right? And this is for first order kinetics. Okay, so I need to integrate this. Let me just write these values. So I'm given R equals 1, R equals 2, sorry, so this is 3. XAF is 0.9, this will be 0.9. This expression here will be what? 2 over 3 of 0.9, right? And this is basically 0.6. And this CA note will cancel with this CA note. And I'm going to move the K next to the tau because I need to compare them anyways. So let's rewrite it. So I have tau. I'm going to call it tau recycle multiplied by K is equal to 3 integral from 0.6 to 0.9 of dxa over 1 minus xa. And this is basically equal to 3 into minus ln 1 minus xa from 0.6 to 0.9. And this will be equal to it. This will be equal to 3 into minus ln into 0.1 plus ln into 0.4, right? 1 minus 0.9, 0.1, 1 minus 0.6, 0.4, minus, minus, plus. So this is what I have. And this will be equal to basically 3. I'm going to combine these two lns, ln. Okay, so this is tau recycle K. Recycle. Tau recycle K. Good. So now let's go for a normal PFR. So for a PFR, first order reversible, we know that the performance equation in this case is what? We already said, you know, we've used it in the past two problems. CAF over CA naught is equal to exponential minus K tau. And CAF minus CA naught, if you recall, is just 1 minus X, right? Because if you recall the definition, it is 1 minus X, because X, 1 minus XA, you know, if you forgot about this, let me just have a little box here at the top, maybe in this corner. Okay, let's write it here. You know, XA is equal to CA naught minus CA over CA naught, right? It's moles reacted over initial moles, which is 1 minus CA over CA naught. So this means that CA over CA naught is equal to 1 minus XA, right? Oops. And this is, you know, just in case you forgot where we got this parameter from. Okay, let me go back here. So 1 minus XA, XA is 0.9, so this is equal to 0.1. So basically, if I take ln both sides, minus k tau is equal to ln 0.1. And, you know, if I take the minus, so k tau is equal to ln 10, okay? So I have k tau PFR and k tau recycle. So we need to find tau recycle versus tau PFR. So I'm gonna just take the ratio over tau PFR is equal to 3 ln 4 over ln 10. And this is equal to 1.8. And this is the answer to this problem. So your recycle actually requires a longer residence time to achieve the same conversion. So in this case, no recycle is actually the better option for this problem. Okay, so this is the answer to problem number 5. Now let's move on to number 6. So let me save, let me clear all the drawings, and let me go back to the homework, right? Okay, number 6 here. The kinetics of the aqueous phase decomposition of A is investigated in 2 mixed flow reactors in series, second having twice the volume of the first reactor. At steady state with feed concentrations of 1 mole A per liter and mean residence time of 96 seconds in the first reactor, the concentration in the first reactor is 0.5 mole per liter and in the second reactor is 0.25 mole A per liter. Find the kinetic equation for the decomposition. So I need to find K. Okay, and I'm being told that 2 mixed flow, second one is twice the volume. Okay, and I'm given that the concentration Ca naught is 1, tau 1 is 96 seconds, and Ca1 is 0.5, Ca2 is 0.25. So I'm given all the concentrations. I'm given the tau in the first reactor, and I need to find the kinetic equation in the second reactor. Okay, so it seems that we're going to use a similar approach. Let's just draw the situation and then plan it. Okay. So this is page 9, I think. And this is problem number 6. So let me draw the case situation here. So I have one CSTR. Don't forget this little mixer. Right, is going to a second CSTR, which is twice as large. And I'm being told it's a decomposition. So always remember that decomposition implies first order kinetics. So decomposition, decay, they're both first order. Something to remember. I'm being told Ca naught is equal to 1 mole per liter. I'm given C1 is 0.5 mole per liter, right? And I'm being told that C2 is equal to 0.25 mole per liter. Sounds good. I also know that tau 1 is equal to 96 seconds. And I'm being told that V2 is equal to 2V1. Okay, because it's first order kinetics, I have minus RA is equal to K CA. I'm looking for K. I need to find K. Okay. So how do we do this? I'm given V2 over V1. So maybe if I say V2 over V1 is equal to tau 1 K over tau 2K, I can solve for tau 2 and then use the PFR equation for tau 2 to get K, right? Yeah, it seems like a reasonable approach. Okay, let's do this. So let's start with the first PFR or first CSTR. So I'm going to call this one, call this 2, right? So CSTR number 1. The performance equation for this guy, V over FA naught is equal to tau over CA naught is equal to XA over minus RA. And this is basically equal to, I'm going to rewrite XA as CA naught minus CA over CA naught multiplied by RA, which is 1 over K CA. Wait, let's go back to the problem. I want to double check. Do they want us to find K or find the kinetics? Find the kinetic equation. Okay, so just be careful. Find the kinetic equation means find the entire expression, not only K. Yeah, so I made a mistake here and said this is first order. We can't really assume it's first order. So usually decomposition would be first order if I write A goes to R, or, you know, if it's given that A goes to R, and a lot of the decomposition reactions are like that. But in this case, you're not being told. So I'm gonna just say that minus RA is equal to K CA to the N. So now I have two unknowns I need to find out, K and N. So just be careful about this. And then it's gonna be K CA N. Okay, so basically, I'm gonna rewrite this. So I'm gonna get tau over CA naught is equal to CA0 minus CA over K CA to the power N multiplied by 1 over CA naught, and this guy cancels with this guy. So I get the general equation is equal to CA naught minus CA over K CA to the power N. Okay. So where do we take it from here? Okay, let's rewrite this. So for reactor number 1, I'm gonna have tau 1 K is equal to CA naught minus C1 over K C1 to the power N, or not K anymore because I moved it to the other side. And for reactor number 2, or for CSTR number 2, I'm gonna have tau 2K is equal to C1 minus C2 over C2 to the N. Okay, so these are my two equations. So if I divide them, so if you recall that tau 1K over tau 2K is equal to V2 over V1, and this is given to be 2. So this will be equal to 2. And if I plug in some of these numbers here, so what do I have? I'm given CA naught is 1, I'm given C1 is 0.5, and I know 0.5 to the N. And here C1 is 0.5, C2 is 0.25 over 0.25 to the N. Okay, let's substitute these guys here. So in this case, I get just be careful here. They're freezing. Yeah, just be careful. To be awake. Okay, here V2 over V1 is actually T2K over tau 2K over tau 1K, sorry, is equal to V2 over V1 is equal to 2. So tau 2K will be 0.25 over 0.25 to the N divided by 0.5 over 0.5 to the N, right? So let me save this. I'm gonna move to the top here. I'm gonna erase all of this junk. Let's continue this problem. This will be page 10, right? Okay. So if I continue right here, so we said that we said that 2 is equal to 0.25 over 0.25 to the n multiplied by 0.5 to the n over 0.5, right? This goes with this, I get a 2. I'm going to move the 2 to the other side, so this is equal to 4. So I get 0.5 to the n over 0.25 to the n is equal to 4, and this is equal to 2 to the n, so basically n is 2, right? So my reaction rate order is 2, so I have n. So now I need to get k. I don't know tau 2, so I can't use this expression. I have tau 1, so I can use this expression, right? So from CSTR1, I know tau 1k is equal to 1 minus 0.5 over 0.5 to the n. This is equal to 0.5 over 0.5 squared, and this is 2 basically, right? And I know that tau 1k is 96 seconds. So this means that k is equal to 2 over 96, which is 1 over, what, 45 and 3, 1 over 48, right? 1 over 48. So I have k and I have n. So this means that my kinetic expression in this case is 1 over 48, and let me just rewrite this. Oops. Okay, 2 over 96, so this is equal to 1 over 48, and the units is second minus 1. Okay, so my minus RA will be equal to is it second minus 1? Let's have a look at the units here. So here I have basically C over C. So this will be mole per liter over mole squared per liter squared. So I'm gonna end up, and this is second. So the units, this 2 is actually liter per mole. I'm dividing by seconds. So this is liter per mole second, which are the units for a second order reaction. So it makes sense. So the final answer basically in this case is minus RA is equal to 1 over 48 CA squared. Okay, so this is the answer to problem number 6. And this is the last one, the homework. So please go over it, try to replicate the solutions, try to understand the approaches as you prepare for your exam and as you prepare these solutions. And if you have any questions, please come to office hours. Try to understand the different approaches we're solving these problems. And next week will be a review. I'll try to go over all the different approaches, all different problem types as you prepare for the exam. Thank you very much.